Well, hello and welcome to this presentation. First of all, thanks for your interest and for dedicating your precious time to this talk. My name is Anthony Boone and I'm currently the digital power consultant with the Embed group at Altair. So I'll just quickly go over the agenda, considering that we have a limited time here. So what we'll do is do a brief overview of battery management systems and the reasons for battery management systems, go over the development hardware that's necessary to develop a real-life system, look at the configurations of that hardware and advantages of doing that for software development, go with the software development itself using model-based software development with Altair Embed, and we'll do the concluding marks. So here's the overview on battery management systems with an emphasis on battery electric vehicles. So the battery pack is considered by most to be the most critical element in battery electric vehicles. A typical battery pack could be rated at 400 volts or 800 volts, so the typical voltages. And in order to achieve these, it's necessary to put many cells in a series connection. For example, a 400 volt system could require 96 cells in series, or a 800 volt system 192 cells in series. And then, of course, each cell, particularly if we use the cylindrical cells like these ones here, they have limited ampere hour capacity, around about 4 ampere hours, maybe 21700s would have 5 ampere hours. And so we need to put many of them in parallel, and a typical BEV would have 80 of those cells in parallel in each series element. So there would be 80 times 96 cells in that battery pack for a 400 volt system. And also we can do battery management systems for the 12 and 48 volt auxiliary functions. So why BMS? Well, normally there's a single charger in a battery electric vehicle, and this charger is rated for the full battery pack voltage of 400 volts or 800 volts in that case. So this charging voltage needs to be distributed across all the series elements in the battery pack. And if we've got 96 series elements, we need to distribute that charge and the charging voltage uniformly across the entire pack. So any non-uniformity in any of the batteries due to manufacturing or due to aging or due to performance decrease of those battery cells, that will cause differences in the charge. And over time, those differences will integrate and they'll become even more significant. And what can happen is we may overcharge one cell, and that can overheat the cell, and if we overheat it too much, we can get thermal runaway, and that could even create a possible fire. For the other cells that are not charged correctly, they'll be undercharged, and you're not going to optimize in any way the ampere hour capacity of your battery system. So a BMS system comes in this way, in that we measure the voltage of each individual series element in the battery pack, and we can make sure during charging that the charge is distributed uniformly among those series cells, and this can be done via cell voltage balancing. We can also monitor the performance of the battery over time during discharging or during driving and during charging, and optimize the performance of that battery pack and optimize the performance with temperature. Well, I'd just like to quickly go over the design objectives. And first criteria for design objectives is the performance optimization. We want to optimize the performance of the battery pack as a whole. So these are many of the requirements for that. Then we have the actions that we will be taking and objectives of that action. So we want to basically optimize the battery pack life want to optimize the energy stored in the battery, optimize the utilization of that energy so that we utilize it from 0 to 100% as much as possible. And in such doing that, we optimize the maximum mileage range of the system. Then we have the safety aspects of the design objectives, very important as well. Requirements, the BMS actions, and the objectives there. And obviously we want to keep the system safe. We want to totally minimize the risk of any fire, minimize the risk of any damage to the system, minimize any risk in the system as a whole. And a lot of that is cutouts and control and protection within the BMS system. So the third group of criteria for design objectives is multi-cell management. We said that in a typical battery pack we might have 96 series elements and 80 cells per parallel system, so that would be almost 8,000 cells in a battery pack. So we need to monitor and manage all of those cells that are connected to a single charger and to a single load, and so we need to distribute the charge uniformly across all those series elements, and in doing so we need to counter mismatches in manufacturing, degradation in lifetime, and degradation in performance over that lifetime. And the typical actions we would do here, we typically to distribute the charge over the cells, we would do cell balancing. That cell balancing can be active or passive. Normally we would use passive cell balancing due to simplicity and greater reliability of that type of balancing. And the overall objectives would be to increase the battery pack as a whole, again, to optimize the energy stored in that battery pack and to utilize the maximum amount of that energy so that we can maximize the mileage range of the system. So for the hardware development, we'll just go over some of the hardware required for developing the software of the system. So the hardware required is obviously a BMS board, and we need to connect to the battery cells, and there are many commercial solutions available. This one is from TI. These boards are evaluation modules, and they're easily obtainable at present, and these can be connected in series. For example, this one can be connected to up to 16 cells. So for 96 cells, we would need 6 of these in series. Same thing for Infineon, which has their solutions as well. Same thing, this is up to 12 cells each, but we can put up to 20 of the chips in series. The ST as well have a solution as well with up to 14 cells per chip and per evaluation board, and up to 15 chips can be connected in series in this case. And there are many others as well. NXP, Analog Devices, Maxim are just some of the others that are examples, and they all do similar things. What is important is that we can do the software and connect to any one of these modules. Well, obviously, to correctly develop the BMS system, we need a battery, and for this reason we developed the battery board, and this battery board is directly compatible with the TI EVM, the evaluation module, and it can be easily adapted and connected to any of the other manufacturers' BMS evaluation modules. So here we have up to 16 series cells. The NTCs in here are temperature measurements, where we can measure the temperature of every second cell, connections to the cells to the BMS system for series cell voltage measurement, etc., etc., charging connection, load connection, etc. Obviously, then we need a microcontroller because we need to control the system. And in this case, we're using the Delfino from TI, the F28379, which is a fairly powerful microcontroller. totally sufficient to do all of this work and more. Other solutions we can do with Infineon and ST as well. And the important part is once the software is done for one microcontroller, with the Embed IDE, we can easily change to another microcontroller with very small adaptation. So some of the hardware configurations that we need to do this software development. So for the first hardware configuration, I'll just quickly go over this setup here where we have 3 battery packs, okay, each of 16 cells, and these are all connected in series here, so we have 48 cells total. And then each one of these has its own BMS board connected to each one performing the balancing of the 16 cells and measuring the voltage and temperatures of those cells. This is connected, the first board is connected to the Embed GUI here, which is communicated over the real-time serial blocks within this Embed IDE, and these are using the USB to serial converter here. And then this would communicate with the other ones via the isolated UART. The isolated UART is necessary because these are connected in series, remember, so the lowest voltage here of this one here would be the sum of this voltage here. So this one would be about 67 volts, and each one would be adding 67 volts to the ground of each of these systems, so that we need this to be isolated. In a 400 volt system, this would go up to 400 volts difference here. And okay. Then in this case, we have the same battery system, the same BMS system, the same balancing and voltage measurement here. What we're doing is we're adding a microcontroller. The microcontroller speaks with the 3 BMS cards here, firstly by the first system, then via the isolated UART to the other systems. The microcontroller can also gather directly the voltage, the pack voltage and current from the battery board itself. It can also control the charger, a discharger here on off, and knowing when to cut it off. It can cut this off and also control the voltage and current of the same. We have the same GUI here, but in this case the GUI is speaking over the JTAG link, and it's running as a hardware and loop type configuration. Additionally, we have a CAN interface here, so we can speak to other systems via CAN and send voltage measurements, alarms, etc., actions of the BMS system. Then we could move on further to that. We could do this as a purely demo system if we need to evaluate different hardware manufacturers here in the BMS system. We could even perfectly set up a system with, for example, a TI system here, an Infineon system here, an ST system here. This is over the SPI in this case, and these 2 systems are over UARTs. This microcontroller is perfectly powerful enough to do all 3 systems concurrently. And it certainly has enough peripherals to do the UARTs and the SPIs and many others as well. Again, we have the same JTAG interface over here. The microcontroller would be running concurrently 3 different systems in this case. It can be isolated in this case, but if we disconnect the series connections and ensure that the batteries are at the same level, for example in parallel, it could be also done without the isolation. And this is a system here, okay? So basically here this is our charger and load in this system here. We have 8 series cells in this case here. The Embed GUI is running here in the background, and this is the TI balancing system. And expanding on that, in this case we have 2 boards here, each with 16 cells. So we have 32 cells and 132 volt battery voltage. We have 2 stacked evaluation modules for the BMS hardware here. They're communicating over this isolated serial link here. We have temperature measurements coming into each of these evaluation boards. And we have the microcontroller running in this docking station from TI. And the microcontroller here is the JTAG link, which is running to the Embed GUI on the PC. And we also have a possibility for CAN connection here. And this is the Embed GUI. This is the main page. Clicking on cell voltages, we get a cell voltage view. Clicking on cell temperatures, we get a cell temperatures view. Clicking on faults, we get a faults view, and etc., etc. So what we will go over now is what we're aiming at with this talk, which is the software development. Firstly, for the software development, we need to know a little about the Embed IDE that we're using, the integrated development environment. And this is just an extremely brief overview. You can get more details at this link here. You can see the blogs at this link here. And I won't go over it here because we don't have time to do those sorts of things here. But this is basically a block diagram environment where we're developing the system and we can do model-based design. Also in the Embed IDE, we have the code generation and embedded design. So we have blocks dedicated for the microcontrollers where we can program the microcontroller and program all the peripherals within that microcontroller. And as such, generate the C code, compile it to the target microcontroller, and do debugging diagrams and production diagrams for that C code, so it can either run with the Embed GUI or independently on microcontroller. Also, as an add-on to that system, we have the Digital Power Designer, and this is mainly aimed at simulating power conversion systems and doing code generable diagrams to be downloaded to microcontrollers to control those power converter systems. Also within this add-on, you'll see battery management system applications. And for more information, you can go to the videos here on this link. So a typical example diagram is the one we've shown before, and this is the Embed GUI that was developed to control and monitor the battery, in this case, interface with the BMS hardware. So if we click here, for example, on the cell voltages here, what we get is a cell voltage view. Okay, so we have all the cell voltages managed, monitored here and reported here, and we also can graph these over time, over the charging cycle, over the discharge cycle, and we can easily change the timing of this and make it much longer as well. We also have blocks for each of the evaluation modules, so this GUI itself supports up to 6 evaluation modules in series. Then we anywhere and we go back to here, and we also see, of course, on the main page the cell voltages reported here in a bar graph type configuration, along with temperatures, minimum and maximum voltages, average cell voltages, other internal temperatures, etc. We can do report the state of the battery when this is running with a microcontroller, for example. Okay, we can click on the cell temperatures here, and go to cell temperature view, and we have all the temperatures of the monitored cells, again for all the EVMs, evaluation modules. We can click, for example, on faults here, and we go to the faults view, and we have all the faults over voltage monitors, under voltage monitors, under temperature monitors, system faults as well, and programmable GPI faults here in this case, etc., etc. Then we click and we go back again. We can right click on this here, and we bring up dialogues, for example, these are configuration dialogues. So here, for example, we're configuring for 12 series elements in the EVM 1, for example. All the other EVMs can be configured as well separately. Balancing configured, whole configuration can be done here and sent to the BMS hardware. Clicking again, and we can go back to the screen. Now, if we double left click here on this block here, we're moving into the diagram. These are all the blocks in here. This is the typical block format of Embed. These are the blocks that are configuring the system. So that these are the dialogues inside here. They will configure the system for us. What we're coming out with are variables here, which are actually the registers for the hardware, the BMS hardware. And these registers values are shown here. And here I have comments basically giving the addresses of those registers. So if we right click on this block down here, we go further down into the system. What we have here is the routine block of the system. This can be code generated, this block here for the hardware target. Down here we have a display interface. So what's coming out of this block here, it goes into the display interface, and this is put into the correct format to displayed on the main GUI screen. Also, we have logging, so the GUI can do logging of the data over long periods of time. Then when we click on the main routine block, we go further down, and the different functions are divided into different sections here. Here in this block here, for example, we're calculating the state of charge, the autonomy of the system, the state of health, for example. Depends on your model use, the way you want to do that. If we click on the COM system here, for example, we see how the communication is working to a basic extent with transmission here, reception here, and we see data that is being received. So if we go back to that, we can now select this block here and then go to CodeGen. And CodeGen here, we can compile here. We can compile for the target, which we said in this case we're using an F28379 from TI. We can compile to this target, and after compiling for that target, we can then pull out, in this case here, a target interface block, and this is it here, which is created identically to the block we've seen here. We replace this block with the target interface block, and now this system is set up to run directly with the microcontroller hardware target in a hill configuration, a hardware in loop. So it will communicate with the hardware target over the JTAG interface. Okay, so this is an overview of some of the advantages of this system. I think you can read them easily here. I won't go over them too much, but I can say that I've been using this integrated development environment for more than 20 years. I just am always surprised by the flexibility and the ease of use of the whole system, and being able to do everything I need in the one software environment. And if you want further details on this BMS system, you can go to this blog here on the Altair community site, or the Embed example diagrams can be found in the Digital Power Designer. Thank you.